Okay, so this is lecture 1.7. For the last 2 or 3 lectures, we have been talking about transfer function representation. We talked about uh, electrical systems and we introduced mechanical systems on the last term. So we'll be continuing with that. So on the last term, we discussed the basic building blocks of translational mechanical systems, right? Translational mechanical systems, and how to write down the transfer function for some simple mechanical systems. Today we are going to see mechanical systems with more degrees of freedom, more complex mechanical systems, and then we are also going to talk about rotational mechanical systems today. Right? So let us come back to the slide that we were looking at on the last turn. So this is the slide. So we were talking about the force velocity and force displacement relationship of translational mechanical systems. Okay, and then we solved a small example in which we had mass spring damper, a single degree of freedom system. So today we are going to see one important thing in this, which is the concept of degrees of freedom. Degrees of freedom is actually the number of linear independent motions possible. So degrees of freedom, when we talk about a mechanical system, is the number of linearly independent motions possible. You can understand it from the electrical system perspective, in the sense that if you have one mesh, then you have only one mesh current. If you have two meshes, you can have two mesh currents even if one of the meshes is open circuited, right? And if you have a voltage source in the other mesh, you can still have another mesh current. So the two mesh currents are coupled. They are coupled, yes, because the value of one sometimes determines the value of the other. But despite being coupled, they can exist independently, right? In a similar way, you can have coupled motions in a mechanical system, but it is possible to have one motion and to not have the other motion, right? They can exist independent of each other. So the number of equations actually of a mechanical system, the total number of variables in a mechanical system, would be dependent on the number of degrees of freedom that it has. So for example, in this case, this is the case in which you have a 2 degrees of freedom translational mechanical system. This slide is from your book, from your textbook. Now, why is it a 2 degree of freedom? Because the translation of mass m1 and the translation of mass m2 can exist independent of each other. They are linearly independent of each other. Right? So how do we know that? For example, if you fix one of the masses, we can move the other, right? So if you fix, for example, mass m1 and you assume that x1 is equal to x1t is equal to 0, that means you have fixed m1. You have to ask this question to yourself: would x2t be also equal to 0, or can it have a non-zero value? So in this case, if you just fix this m1, assume it to be a wall, you can still have the motion of mass m2 possible. You can move it on this side and compress this spring, and you can move it to this side and compress this spring and damper. In a similar way, if you fix the other displacement, in the sense that you don't allow m2 to move, you fix m2, then you have to ask yourself, if I make x2t is equal to 0, can I move x1? Can I allow the displacement x1? And the answer is yes. You can still move this mass around. So this tells you how many degrees of freedom does this mechanical system have, And when you know the number of degrees of freedom, you can write down the equations of motion. And this also helps us in writing down the equations of motion more easily, because what we can do is to, because it's a linear system, we can assume one motion exists, right, and write down the forces and make the free body diagram for one mass, and then assume that the second motion exists and draw the free body diagram for the two masses. Basically, this motion, the motion x1t, causes certain forces to be exerted on m1 and to be exerted on m2. In a similar way, the motion x2 causes certain forces to be exerted on m1 and causes certain forces to be exerted on m2, in addition to the external force that is acting, which is f of t. And these motions being independent of each other, so you can apply the principle of superposition and assume that in the first case, let x1 t, for example, be equal to 0, and let us see what are the forces if x to t is not equal to 0. And in the second case, let us assume that x1 t is not equal to 0, and let us see what are the forces, right, when this case is there. So these are two cases, and the total force that will actually act on both the masses can be obtained by summing up the forces that we get here and summing up the forces that we get here, right, on both the masses. So this is the procedure that we'll be doing in this. So let us look at the so in the beginning, let us assume that only x1 x this is the first case, right? So x1t is not equal to 0 and x2t is equal to 0. So what are the forces on the two masses when only mass m1 moves, right? So if you look at that, at the forces, I think it will be very, you can easily see that if this mass moves, what is going to happen? And you have to assume motion in the positive direction, so that is why the directions are shown, right? Because you'll be writing the equations of motion for x1 and x2 defined like this, right? So you're assuming that it doesn't mean that the direction is like this. It means that the positive direction is assumed to be this direction, right? Just like you assume directions for currents and voltages. So if you assume a motion in the positive direction, what are the forces going to be? So this spring is going to be extended, this damper is going to be compressed, this damper is going to be compressed, and this will have its own motion, m1. It will resist the motion. So if you want to write down what are the forces on m1 for this case 1, you're applying a force, and you write down the equations of motion in the s domain. You write down the forces in the s domain. So you're applying a force f of s, and now what are the retarding forces that are acting? So this spring is acting. This spring is acting in opposition to this motion, right? K1. So you can write S. Just a second, let me see. K1 x1 is, sorry. So this is proportional to the displacement. So K1 x1s, right? It's retarding the motion. And what else is retarding the motion? And this spring which is on this side here is retarding the motion. So SFV3 x1s would be the retarding force because of the damper here. And what is the retarding force because of this spring here? K2. So it will be K2 x1s, right? And you also have this friction here, which is shown with the friction with the surface, right here. So you have a retarding force because of that, which is SFV1 x1s. So this is the retarding force because of this friction. And in addition to that, you have a force because of retarding force because of the mass m1, which is going to be s car m1 x1s. So these are the forces that are going to act on m1. Let us check whether we have drawn all the forces correct. Yeah. So these are the 6 forces that are acting and all these elements that are connected to M1 are basically pushing it back, right? Trying to resist the motion x1. Now this is for this motion when there is x1 and x2 is not equal to 0. In this case, what are the forces on M2? Is there any force on M2? M2 is stationary. There is no motion of M2 because we have assumed that this x2t is equal to 0. But despite the fact that it is stationary, it is possible that there would be some force on it, right? And yes, that there is a force on it. Why? Because you actually have this damper here, which is connecting M1 and M2, right? This damper here, which is connecting M1 and M2, and this spring here, which is connecting M1 and M2. Both these are actually getting compressed, right? Because they're being pushed by M1. So when M1 is pushing them, this force is actually going to transmit to M2, right? This force is going to transmit to M2, right? So there would be a force on M2, and that force is going to be the transmission of the force SFV3x1s, right, and K2x1s. So the displacement x1s, which is basically the displacement of M1, is also causing a force to act on M2, and these forces are towards right, because when you compress this spring here, right, you compress it, it is going to exert. When you compress the spring, any spring, you're trying to compress it, it's going to exert a restoring force like this in this direction, and a restoring force like this in this direction. And these two forces are going to be equal, right? So that is why you have the same force K2x1s here as you have K2x1s here, but the directions are different. And the same force SFV3x1s here as SFV3x1s here, but the directions are different, because these forces are now actually pushing the mass, would actually try to push the M2 mass towards the right? But because the mass does not have a displacement, we have already assumed that x2t is equal to 0, which is your case. So there is no action of this spring, because this spring will not be compressed. There is no action of this friction, because there is no displacement, and there is no action of this mass in this case, because there is no x2t. The only forces acting on M2 are the forces because of the displacement of My. So I hope this is clear. It's very important to understand this. This is a very basic and a fundamental concept when you try to solve mechanical systems. So if you have understood this, I think we can see that the two cases can be drawn like this, the way we have drawn that, right? So this is the case. This is the first case when you have x1 s not equal to 0 and x2 s equal to 0. In a similar way, you can draw the second case. The second case is going to be when just let me stop this. The second case is going to be x2t is not equal to 0 and x1t is equal to 0. So you are fixing this mass and you're allowing this mass to move. Now in that case, what are the forces going to be? Now see, you can see very clearly that if you allow this mass to move, M2 to move, right? You have to assume that M2 moves in a positive direction. You'll say there is no force on M2 directly. How will it move in the positive direction? You can always have a non-zero initial condition, right? So M2 is already displaced in the positive direction, and because of that, it moves in the positive direction, right? So you can always decide that one of the two moves, even if there is no force directly on the other. So if M2 moves in the positive direction, so this is going to be compressed and it is going to retard it. This is going to be extended and this is going to retard it, right? This is going to be extended and it is going to stop it, try to stop it from moving. And so is going to, so is this inertia, this friction here, this is also going to stop it from moving. And this mass, its own mass, M2. So these are the 5 forces, 1, 2, 3, 4, 5, that are going to act in the opposite direction, right? So let us see on M1. So let us see, do we have these forces? Yeah. So these are the 5 forces on M2, right? Which are trying to retard the motion of M2. You can see that there is no external force directly on M2. That is why it is not sketched, right? Okay. Now coming back to the original diagram, what are the forces on M1 now? So these forces actually, which are between M1, because of the elements between M1 and M2, because of this damper and this spring, these are actually going to act on M1. So if we are actually compressing this damper and we are compressing this spring, that means we are actually trying to push this M1 to the left hand side. So there will be 2 forces on M1 which will try to move M1 to the left hand side, right? So that is what we have here. Not to the left hand side, to the right hand side, because this M2 is moving towards right, so this damper is being extended like this, right, and the spring is being extended like this. So because of that, these 2 forces will try to push this mass M1 to the right hand side, right? So although the forces will oppose M2, right, the motion of M2, so it is like this spring, right? The spring being extended, trying to extend the spring on this side. So what it will try to do is, on this end, it will try to exert a force like this, restoring force like this, and on this end, it will try to extend a restoring force like this. And if you try to extend a spring, compress a spring, so you're trying to compress a spring. This is like extending the spring. If you try to compress the spring, then it is going to push this side on this and this side on this. So in this case, when you're saying M2 is moving, what you're trying to do is to extend the spring. And when you extend the spring, it is going to exert a retarding force in this direction on M2 and a pushing force, right, on this direction on M1. So that's why you have these 2 forces here. So this is the diagram of forces on M2 because of the motion of M2, right, and forces on M1 because of the motion of M1. And then you have the second diagram in which you have forces on M1 because of the motion of M2, right, and forces on M2 because of the motion of M1. So what we basically do is to add all these forces up. So all the forces on M1, which are the sum of the 2 forces, force because of the first case, when you said x1t is not 0 and x2t is 0, force acting on M1 in the second case, and you just said that x1t is not equal to 0 x1t is equal to 0 and x2 is not equal to 0. So this is the total force, the free body diagram for acting on m1 because of x1, because of motion x1 and x2 together, right? And similarly, you have this total force acting on m2 because of motion x1 and x2 together. And then when you have these two equations of motion, you can easily write down the transfer function, whichever transfer function you want to write, right? Because you have two equations in two variables. You have m1 x1 as one variable, x2 as the other variable, and you have two force balance equations. So in this first case, you will be writing Fs is equal to the sum of all these, the forces in the, acting towards right and the forces acting towards left have to be equalized, right? So if you have to write down the equation of motion from the free body diagram that you have drawn here, you will say Fs plus K2 X2S plus F V3 S X2S is equal to K1 plus K2 X1S plus FV1 plus FV3 S X1S plus M1 S square X1S. So you're summing up the forces that are acting towards right and summing up the forces that are acting towards left and equating them. So you get this. This is one of your equations. In a similar way, you'll get the other equation from the other free body diagram, which is here. So in this case, you'll be writing K2 plus K3 X2S plus FV2 plus FV3 SX2S plus M2 S square X2S is equal to FV3 SX1S plus K2 X1S. So you get two equations and you get two variables, X1S and X2S. And then you can find out the transfer function, whether you want to find out X1S by f of s, because f of s is the force that you're applying, or you want to find X2S by f of s. You can eliminate the variables using Kramer's rule and find out the answer. Okay. So in a similar way, you can have a higher degrees of motion system. Like for example, in this case, we have a 3 degrees of motion, freedom translational mechanical system. And why is it a 3 degrees of freedom system? Right? So the first thing that we have to do is to identify the number of degrees of freedom. Why is it a 3 degrees of freedom system? Because see, this block on top is free to move on these blocks which are there, right? So its motion is independent of whether the blocks below are moving or not. Okay? So if you fix blocks M1 and M2, you can still move block M3, right? And the forces acting on block M3 would be the frictional forces because of the because it is actually put on two other blocks, right? And suppose you fix block M3. So if you fix block M3, can you move if you fix block M3 and block M2, if you fix these two motions, can you move M1? The answer is yes. You can still move this around. Because the spring can be compressed, the spring can be compressed, and this motion is possible. In a similar way, if you fix M1, can you move M2 around? Yes, you can. If you fix M1 and M3, you can still move M2 around. So you can easily see that there are 3 different motions possible, 3 degrees of motion possible in this. And you can write down the equations of motion for this 3 degrees of freedom system. And what's more interesting is you can also write down the equations by inspection in this, right? Just like you wrote down equations by inspection in mesh analysis. And for that, the rule is same. So what is the basic structure of the equations that you get, right? In a translational mechanical system, you get this impedances, right? Which is impedance matrix, which will be F square M S F V, which will have these terms, right? and K, these three terms, mass, in damping, right, and spring. And this multiplied with X, the displacement vector, is equal to the force vector, the forces that you are applying. So you can write down the equations by inspection by looking at first the three displacements and what are the impedances connected to the three displacements, right? And then writing down the impedances connected in between the displacements, right? So if you take this example and try to write down the equations by inspection, uh, how will this be, right? So let me draw this matrix here. Okay, so this is going to be x1s, x2s, x3s. These are the three displacements, and this is the impedance matrix here. It's a square matrix, and on the right hand side you have the forces that are acting externally on this. And in this case, is there any force that is shown on this? Yes, the force is here. It is acting on the second displacement. It is causing the second displacement directly. So you have this F S here, and there is no force directly on this mass. There is no force directly on this mass. So there are no forcing functions here. Right? What are the impedances that are connected to only the first displacement xy? So now let us look at this more clearly. Right. Let me wrap this up. And okay, so what are the forces that are connected? What are the impedances, right? We call them impedances because of the analogy between this and the electrical system, right? So what are the impedances connected to only x1, this displacement here, right? So x1 is connected to k1, it is connected to k2, it is connected to SFV3, it is connected to uh, its own mass, right? It is connected to this. So these are the impedances that are directly connected, right? So this element here, if I call this, because the space is limited, if I call this asterisk, this element, the 1 element here is going to be K1 plus SFV3 plus FV1. So these are the two frictions, plus K2, this one, right, plus F square M1. So this is all the impedances that are directly connected to the x1 displacement, right? Similarly, what are the impedances that are directly connected to the second displacement, which is x2? So if you look at that, you can see that x2 is directly connected to its own mass, right? So the second diagonal element is going to be S square M2, and then the friction here and the friction here plus SFV4 plus SFV2, right? And also the spring here. The spring is directly connected plus K2. So this is going to be this the 2 element here. In a similar way, what is the 3 element here, right? So what is the 3 element? So the 3 element here is going to be, what is the impedance that is directly connected to M3? M3 is connected to its own mass, so S square M3. We are talking about impedances which are related directly to X3, connected to X3. So its own mass M3 plus this friction here and this friction here plus SFV3 plus FV4, right? So these will be the 3 diagonal entries in this matrix. Now let us take any one off diagonal entry and see what it's going to be. So what is this entry going to be? Right, the dollar sign. The 1-2 entry. The 1-2 entry is going to be the impedance that is common between 1 and 2, displacement 1 and 2. So what is common between displacement 1 and displacement 2? Right? What is connecting displacement 1 and displacement 2? Is there any direct connection between these two? What is common between these two is this spring here. And you can also see from these equations, right? What is common between these two? So you have K1 here, you have V3, you have V1, you have M1, you have K2, and similarly you have M2, V4, V2, you have K2. So what is common is K2. So this is going to be K2 with a minus sign, the dollar. In a similar way, what is common? What is common between and so this is going to be a symmetric matrix. So the 1-2 element is going to be equal to the 2-1 element. In a similar way, what is common between what other sign shall we make? Okay, so let's call this alpha. What is common between 1 and 3? Is there anything common? Because this is the 1-3 element. What is there anything common between 1 and 3? Yes, this friction is common between 1 and 3, right? So this is also evident from the equations 1 and 3, K1, Fv3, Fv1, K2, M1, M3, Fv3, Fv. So this is common. So the 1-3 element is going to be minus Sfv3, right? So and this is also equal to, because it's symmetric, 1-3 element is equal to the 3-1 element, so it's here. In a similar way, what is common between, let's not take some other color, right? Okay, so what is common between 2-3? Is there anything common between 2-3? Yes, between 2 and 3 you have this friction. Between displacement 2 and displacement 3 you have this friction, right? This friction Fp4. So this element beta is going to be minus Sfp4. So you have this whole matrix here, right? And you do not have to, although drawing the free body diagram is important to understand the forces, but just by inspection you can write down the equations directly. And once you write down the equations directly, the next step would be to find out any one of these three displacements in terms of the forces using Kramer's rule. And you can have any transfer function that you want, whether you want x1s by fs, x2s by fs, or x3s. So I hope it is clear. What is going to help you is numericals that you solve which are related to this, and there are plenty of examples given in the book. Thank you very much for listening.